Yes, after the lesson we can do makeup.
But I just said fantastic because it makes sense.
Oh yeah, it's a stick. Fantastic.
An orange fantastic.
Yeah, you are orange fantastic. Orange you fantastic? Orange you fantastic. You are what? Orange soda stick? Yeah. You are orange soda stick. Yeah. I didn't write that. That's not. So, you have a calendar there, right? This unit goes past spring break, but there's a few days before and one day after to sort of absorb the weirdness of spring break. Like, for example, if people leave a day or two early, or that we have one day scheduled when we come back to sort of review what we've already gone over, and then we test that Wednesday after spring break. Um, this Thursday, if you're looking at your calendar, you have a quiz. This is your last major grade for the quarter besides your project, which I'll have graded as soon as possible. So if you're trying to bring up your grade, get ready for this quiz. Quizzes are 30% of your grade, so that's significant. And then we've just got, well, I felt like I was going to say something else. I think that was it. Oh, I know what I was going to say. So by the end of next week, that's right before spring break, that's also the end of the quarter. So any makeup work, late work, retakes, corrections has to be done by then. Okay. What we're doing today is, or what this entire unit about is solving systems of equations. A system of equation means just two or more equations together. So systems are 2 plus equations. The reason why we care about systems of equations is in case you're dealing with a situation where there's multiple variables that you're trying to figure out. You know, when an equation has just one variable, like something like this, you just need one equation to figure out what x is, because you would just subtract 5 from both sides, divide by 2, and you would have your answer, x equals whatever. But when you throw a second variable in there, it doesn't matter what math you do. You could move your 5y over, divide by 2, that's what you would have done before, and now you would have this, which is less than helpful because you don't know what y is, right? So what you need then is a method for solving for multiple variables. And the basic idea is that if you have 2 variables, you need 2 equations. If you have 3 variables, you need 3 equations, and so forth and so on. And so that's what we're going to begin talking about today. The good news is you've done this a lot. You did this in Algebra 1, you did this in Algebra 2. And if you've had pre-cal or anything, I'm not actually sure, but I would imagine, yes, you probably did it there. It's a very common algebra thing. What we're going to do is actually start on the back of your notes with the graphing first. We're learning 2 methods today, substitution and graphing, but somehow the notes are out of order, so it's better to start on the back with this problem. So notice this one isn't actually asking us to solve. It's saying, basically, figure out if this is a solution to that system. And how do you always try and check if something is a solution or not? What do you do with it? You substitute it back in. But we have 2 different numbers here. Which of these is going to go in for x? The first one, right? Because that's your x value. And the second one is y. The thing, though, about checking a solution in a system is this. It has to check for both equations, not just one or the other. It has to satisfy both at the same time. So here's how you would do the first one. You would have 4 times x, which is 1/2, plus 15y, which is y is 1/3. And what is half of 4? 2. What is 1/3 of 15? And is it true that 2 plus 5 equals 7? So far, so good, okay? But that's not good enough to just answer yes is a solution. It also has to check out on the second equation. So you take a second, plug it into the second equation, and see what you come up with. A half of 8 is 4. A third of 21 is 7. It is absolutely true that 4 plus 7 equals 11. So the answer to this problem is just yes, because it is a solution. If it had failed the second equation, you would say no. Okay, it's not a solution, because right now we're talking about the system as a whole thing. So both equations at the exact same time. So now that we know the basic idea about how a solution works in the system, we're going to find our own solution. And the first method is by graphing. Okay? So here are the steps for graphing. The first step is to rewrite each equation in slope-intercept form and graph it. So let's do a real quick review of slope-intercept form. You actually have learned in the past several versions for linear equations. This is just one of them. It looks like this. And we call this slope-intercept form because when it's written like this, there's two things that are really easy to read right off the equation. The y-intercept, which is b, and the slope, which is the m. And here's how you use that form to graph a line. Your first step is to graph the y-intercept, the 0, and then the number is whatever's in this spot right here, the b. That's 1 point, but how many points do you need to graph a line? 2. So then that's where the slope comes into play. Your slope is your rise over run, and you use that to graph your second points. And there's a few things about rising and running that I'm going to remind you about when we do this problem. And your second step is to find the point of intersection. That will be the solution to your system. The point that satisfies both equations. All right, so let's practice. Step 1 is to write them in slope-intercept form. You have to do that for both equations. So starting with the first one, slope-intercept form looks like this. That's our goal, to get this equation to look like that form, which basically means you're solving for y, you're getting it by itself. Well, there's two things happening to the y right now, a times 2 and a plus 5x. Which one do we want to undo first? Who's saying something? Yeah, subtract the 5x. We'll take care of the plus 5x first, right? By subtracting it. Thank you. So that gives me 2y equals, and I'm going to write the x part first so I can get it close to that form over there, mx plus b. And y is not solved for yet. It's still times 2. So the inverse of times 2 is what? Divide. And divide both of these things over here by 2. So I have y equals negative 5/2 x minus 1. Yay. And here's what we're going to do with that. We're going to graph the y-intercept first, and then use the slope to get the second point. Which thing is the y-intercept, the 5/2 stuff or the negative 1? Negative 1. So drop a point right there, negative 1. 0, negative 1. Now here's how you use the slope for your second point. The slope is the negative 5/2. What does negative 5 rise in the rise direction mean you're going to do? down, right? So the negative means go down. And a positive 2 in the run direction, run is left to right, and you're going to go right 2. And where do you start from, this point or the 0, 0? Where do you start from? Do you remember? Not the 0, 0. You want to start from your y-intercept, from any point on the line. So starting here, at my y-intercept, I'm going to go down 5, right 2. And now I have 2 points, I can draw my line. But actually, before I want to do that, I have to remind you about something. Going down and right gives you the same line as if you went up and left. You see that? That would all still be points on the same line. So here's why that works. Because negative 5 over 2 is the same value as if the negative was on the bottom. And then now that would be a positive rise. That would be up 5, left 2. So you have to be comfortable going in either direction. And now we have this line here. So you go ahead and do the other line. So we have this. 10 is the thing you want to handle first. It's your y-intercept. Now, it kind of goes off the graph, but that's okay. We can handle that. So there's my 10. And then the slope is 3. Well, let's talk about that slope for a second. I just told you, or I reminded you, that slope is rise over run. Now, that's a fraction, but the 3 doesn't look like a fraction to me. It's really over 1. And that means starting at my y-intercept, the 10, has to go up 3, right 1. But for this particular graph, that's not very helpful. To go up 3, right 1, I'm trying to figure out where these two things intersect. Up 3, right 1 forever is not going to get me anywhere helpful. So I'm going to go the other direction. Instead of up 3, right 1, I'm going to go down 3, left 1. See, it's the same shape, but now it's just the other direction. And then down 3, left 1 gets me here. And the reason why that works mathematically is because positive 3 over 1 is the same value as negative 3 over negative 1, because negative divided by negative is still positive. That goes down 3, left 1. So remember, be able to go in either direction, depending on your needs for a given situation. And the answer to your problem is not this graph. This graph is just your work. It's just your method for solving. Your actual answer is this point right here. And we write points as ordered pairs. Okay, that is your answer, with parentheses and everything. So please remember, when you're writing your answers to solution or systems, you write them as points ordered pairs. Any questions about this? Or anybody needs to slide up again, or you're all good? Okay. This last thing on the back that I want to talk about is the 3 different kinds of solutions you can get to systems of equations. These are the technical terms for them, and I'm going to tell you just a simpler way of remembering what they're saying. Consistent and independent says if you have one ordered pair solution, that means, so like this one had only one solution. It's where they intersect, and that was their ordered pair. So this is saying when you only have one solution, because they intersect. the second situation, inconsistent and independent, this is where the lines don't intersect at all. Do you remember what we called those lines in geometry? What kind of lines don't intersect? Parallel. Right? Parallel lines don't intersect. So if they don't intersect, how many solutions will there be? 0, right? None, no solution. So this would be the kind of system where there's no point that would satisfy both equations at the same time. So one solution, no solution. What other things have we seen before when solving? Same line. If two lines actually are the same line, how many places are they intersecting? All of them. So how many solutions would they have? Infinitely many. And this comes about when the lines have coefficients that are multiples of each other. So they would have different numbers, so they would kind of look different on the surface, but if you were to solve for y and put it in mx plus b and simplify, they'd end up being the exact same line. So that is the graphing segment of our lesson for today. Let's turn to the algebra part. This next method is substitution. So that's on the front of your notes. And we'll go through the steps as we solve the example problem. So look at the example problem. The first one, this one. It's a system because there's two equations. We won't be graphing it to solve. We're going to use algebra instead. Read step 1 to yourself. I love algebra. Read step 1 to yourselves in your brains. Step 1 says solve one equation for either x or y. It does not matter which equation you pick. It does not matter whether you pick x or y. However, some situations are easier than others for your math. So that's why it says one without a coefficient is always easiest. So in this example, I want you to find the variable that does not have a coefficient in front of it. Do you see it? Which variable doesn't have a number in front? X in which equation, top or bottom? Okay, top. It really does have a 1 there, but here's why this makes it easy to solve. Because you would never have to divide off by the number in front. And so that makes your math easier. So here's what step 1 looks like for this problem. We're going to solve for y. I'm sorry, I just made that up. We're going to solve for this x right here. So we're solving for that. This has one step. What do I do to both sides? I'm not plugging in yet, so I'm solving for the x value. That's okay, thank you. I'm glad that you said something. If I'm solving for x to get it by itself, add 2y, right? Add 2. So x equals 2y plus 7, which is grand. Now read step 2 to yourselves. Step 2 says in the other equation, okay, in this particular example, we solved for x in the first equation. So when this says in the other equation, it means in the second one, the bottom one. replace just the variable you solved for with what it is equal to using parentheses around it. Here's what that's telling you to do. In the other equation, which is this one, substitute what you solved for x. So we got x equals 2y plus 7. X equals this. Substitute it in the other equation for x. If x equals that, then I can replace x with that. They're equal. So I'm going to take 2y plus 7 and substitute it right there for x. And that's why this is called the substitution method. So this is step 2. 3 times x, but now x is 2y plus 7. And this is why you need parentheses. That reminder about parentheses is in your notes. So 3 times x is now 3 times 2y plus 7. And then the rest of that equation just stays the same. Plus 4y equals 31. Okay. So now this is the money part of the whole situation. There's no longer 2 variables in this equation. There's just one, just a y. And so now we can solve and actually get a number for it. So that's step 3. You have to distribute that 3 first. So that's 6y plus 21. And then what can I do next on that left-hand side? Add the y's, right? Combine your like terms. So that's 10y plus 21 equals 31. Subtract 21. 10y equals 10. Divide by 10. Y equals 1. Which is great, but it's only half my answer. So read step 4 to yourself, please. Step 4 says go back to the equation you solved for in step 1 and find the value of your other variable. Here's what that means. This highlighted stuff right here is what I did in step 1. Now I know, though, that y equals 1. So to solve, x is already solved for here. When I plug 1 in for y, it's real easy to do the math and figure out x. X equals 9. Now, technically, you don't have to plug 1 in here. You could plug it anywhere to the original equations and then solve for x. But this will go way faster because you already solved for x there. So it's just easier. And the last step is to do what? Read your last step. Yes, ordered pair. Which was x? The first thing we found or the second thing we found? The second thing. Okay. So be careful when you're going to write your ordered pair that you don't necessarily write it in the order you've solved for, but that it's x first and then y. So you take a few moments and do that last example with the decimals. The decimals don't change anything about those steps. You still do the steps exactly the same. Where was the easiest variable for solving? The y in the top one, right? So you subtract 0.8 x from both sides, and you have y equals negative 0.8x plus 7.4. You take that and you sub it in for y in the other equation, right there. So now I have this. Then you do what with that 1.5? Starts with a D. Distribute. Distribute, distribute. And you go tap, tap, tap on your baby calculator. And you get 1.5 times negative 0.8, which I don't know. I don't remember what that is. Negative 1.2x. So I'll change this to subtract. And blah, blah, blah. 11, positive 11, I don't know what I'm trying to say. Just ignore me. And what can you combine on that left-hand side? The what's? The x's. So that's negative 0.6x plus subtract 11.1 from both sides. Divide by negative 0.6, and you get positive 3. So that's great, right? We got x equals positive 3. Now we need y. So this was step 1. This was step 2, plugging it in. Step 3, solving. Step 4, take that x equals 3 and plug it into whatever you got in step 1. So I had y equals this. I'm going to plug 3 in for x now. And a tiny bit of math later, you get 5. And step 5 is to write these as an ordered pair. Which comes first, the 3 or the 5? The 3, because that's your x. Okay. Hopefully all that came back to you from your previous math courses.